I have a shocking announcement to make, and that is the beloved kinetic energy formula 1 half mv squared is in fact wrong. Now, I'm just as surprised as you about how this could possibly happen. And this all arose from a debate between myself and another YouTuber, DraftScience, who has uh, asserted that, yeah, that this is wrong. So, but he had absolutely the correct point that no one seemed to have actually executed a proper experiment to either confirm or deny this formula. But after working with this experiment for an entire week, I can say pretty confidently that, yeah, if you run an experiment trying to test this, you find out that no, it's nowhere near mv squared. And I should know. I'm no dummy. I went to school at MIT. See, there you go, MIT. Whenever the Wakandans need a really smart guy, they go to MIT, and that's where I'm from. So I'm smarter than the average bear, and I'm well versed in experimental protocols and data analysis. And I can tell you, I've looked at this every which way, and must conclude that the kinetic energy formula is not that. It's actually much closer to linear mv, which we commonly refer to as momentum. Now, the way I've done this is I had to design an experiment that can actually directly verify this. So I have to be able to not only get something moving, but then I have to have a way of determining how much energy I put into it, what its precise velocity is, and a way to actually measure how much kinetic energy is in the object. So the only other experiment that had ever been done that was used to initially justify this formula was that they dropped a clay ball and they dropped it onto a clay surface, and then they measured, how much did the ball displace the clay, and they used that as a measure of kinetic energy. Although I think Gary rightly brings up the point of, clay may not be a linear uh, medium. I mean, how do we know that the volume displaced there is the same? And would it be the same if you did it with water or concrete? It would just bounce off, and in which case, obviously the displacement would be zero. So I came up with a different way. Now, I did do a preliminary video on measuring the kinetic energy formula, and but I only did it with a very small distance. It was done just overnight, and I only had very few data points. But the principle is very simple, so I'll re-explain that. So what you have is that you set up a ramp. So there's a ramp. So there's the ground. And what we can do is that we can measure the height here. There's your height. Now, so far as the amount of energy we're putting in, I believe, and this is one of my assumptions, is that this corresponds proportionally to how high you put it in. Now, the way I justify that is that if I had something that's going to lift my object, in this case, I have a little car. Right? There's a little car. And if I had a hand crank or a motor, if it takes a constant amount of energy for me to raise it up, say, this distance. And then if I were to raise it to twice that distance, I would have to crank that thing twice as long. And if I had to crank it, 4 times as high, it would take 4 times as amount of energy. So the energy input is going to be proportional to the height in that case, okay? So we can know what the input energy is just by the height. Now, as a practical matter, I don't want to just drop my car and let it hit the floor. And plus, there's no way for me to measure how much energy is in that car if I did that, right? The easier way is to put the car on the ramp, let it roll down the ramp, and hopefully the presumption is it's going to gather all of the energy it got from the height. And then when it hits the level ground, it's going to roll forward for some time. Now, the question is, how do we know how much kinetic energy is in my little car here? And the presumption is that as the car rolls, there's going to be rolling resistance. And assuming that the rolling resistance is constant, and that's another assumption we will have to and do test, the distance that this thing rolls is going to be proportional to the kinetic energy. So we're going to say the kinetic energy is equal to the distance. Once again, presuming not unless, as Gary says, friction lies. Okay. But so we have to look at that and make sure that friction is not lying to us. But let me show you a video about my new setup here. And I'll show you what is new and improved. Okay. So there we go. There's my video. So let's go ahead and, well, actually that's a different part of my video here. That's another experiment that shows the measurements. But let's see, just one moment while I dig up this video that I've got hiding here. Okay, here it is. Here's the video I want you to take a look at. This is my new improved kinetic energy testing setup. So I have increased the size of the ramp by double, and I now have 6 possible positions here. 1, 2, 3, 4, 5, 6. And I do have a 7th position, but found that my car, when I ran it down, exceeded the length of my hallway. So this is about as much as I can do. All right, so that's the experimental setup. And as you could probably see in that particular run, that wasn't a very clean run. The car kind of ran into the side. And yeah, when you're doing experiments, things like that happen. So you have to repeat the experiment over and over and over again. And even when you do that, you'll find that you kind of get different numbers. And so part of the reason I'm doing this video is to also show you good experimental procedures and to show you that you can conduct actual groundbreaking physics experiments without spending $1 billion on a particle accelerator. These are things which you can do at home. And so as I mentioned, I went and I did numerous, trials, and I had to try and pick out what I thought were the most reasonable values. You could either average the trials, or what I generally did is that I picked the value that was most repeatable. So if I got the same distance several times, that is the distance I used. Now, the other thing that, say, the people 100 years didn't have are these sophisticated, high-speed, high-resolution cameras, okay? Because this is another problem that my initial experiment, I didn't have any way of measuring the actual velocity, because you have to have a high-speed camera and you have to then step through it frame by frame in order to actually determine the velocity. And there was a lot of trial and error with that. I tried like the several settings on the iPhone, but finally I settled on using this GoPro clone, which can do up to 90 frames per second. Okay, so something like this would not have been available to anyone just even 10 years ago, let alone 100 or 500s of years ago when they first came up with this thing. Right, this is actually pretty difficult to test without a modern high-speed camera. So let me bring back my other video that I had that shows how this looks when you test this thing with a high-speed camera. Okay, once again, I have to go dig around and find my video that's around here somewhere. Let's see here. Oh yeah, here it is. It's on the screen already. So I have this set up. Let's see if we can see there's the car going flying by. Okay, so you can single step this thing, and you can see that what I did was I would wait for the car to get off the ramp, and then I would there's a very clear line between the white and the red of the car there, and then I would flip it forward a couple of frames, like 1, 2, 3, 4, 5, and I would measure the distance covered by that, those 5 frames, and then using that, I can directly determine the velocity, and so I directly measured this on the screen in say in the distance of like millimeters or so. So when you see my data, that actually kind of refers to a direct millimeters per unit time, which is the same there. But so I did all of that careful analysis and gathering of data, and then yes, it took a long time to gather all of that data, a week, and I came up with this data. I've got it all nicely graphed out here. And the bottom line is, okay, what you see here, this blue line here, this is the actual data that I took. And you can see that we have on the bottom axis, this is velocity. And on the y-axis, we have distance traveled in inches. And what we can see here is that the blue line is pretty linear, right? It's like, that's a pretty straight line. And straight lines are meaning that the distance is proportional to the velocity. In other words, the measured kinetic energy out of the car is mv. Now for comparison, I have this other orange line here. Now, this orange line is the prediction of what you would get if the kinetic energy formula was in fact mv squared. So for like the first 2 points here, they're pretty much identical. You really can't tell the difference between mv and mv squared for a speed difference this small. But when we get to the 3rd, 4th, 5th, and 6th data points, the difference becomes quite dramatic. Okay, so this would be what mv squared would be. And for example, I have my mv squared result over here, and if it went 60 inches at the first position, which is 5 inches in height, it should have gone 540 inches. Instead, it only went a measly 318 inches. So this is the primary reason why I feel that the kinetic energy formula cannot possibly be mv squared. So I also asked the question of, well, what is the actual kinetic energy formula? And I tried a couple different things. So interestingly enough, you can't actually just do a linear formula on this. V times some constant is going to be the distance, because this line here actually intersects the zero at a velocity of about 2.3, 2.6, right? Which I thought was a little bit strange. You'd think that if it was linear, then it should start at zero. So if you're at zero velocity, you should be able to get 0 inches. But I think that may be because when you have a car like this, the thing is that if you're pushing it really slowly, it's going to just immediately stop, right? Because the friction on this thing is so much that it's not going to have enough momentum to go further. So I'm kind of thinking that's what we're observing there and how that kind of physically makes sense. But in terms of finding a formula that will exactly fit this line, it means I actually have to take the observed formula and I have to basically reset the 0 point by subtracting out where the zero would be and then multiplying it by what the actual slope is. So the actual slope is about 25 inches per increment in velocity. So the formula that I got by just kind of messing around and doing best fit is like you take the velocity minus 2.6 and then multiplied by 25.5, and then you get this yellow line. So this yellow line fits the data pretty closely. So that's this column of data here. So, it comes out pretty close. Instead of 318 is 315, 267 versus 264. So that's pretty close. So that can fit a linear formula very carefully, but essentially the kinetic energy formula should be some constant mv is what you can get. Now, just for laughs and giggles, I also tried to see whether it fitted some other exponential rate. So I tried raising it to 1.5. So if this would be kinetic energy equals some constant mv raised to the 1.5, just to see how that worked. And curiously enough, that also seemed to be very close to the observed patterns, and I believe that is what this little gray line is here. So, but all of these fit the data points very closely, and it's nothing close to mv squared, which is this orange line. So maybe you think I did something wrong. So, one of the main concerns was, how do we know that the drag on this car represents anything constant? Maybe we got this result because when I launched it at this height, the the drag was so much, the friction was so much that it drug at this point down to there, right? Just coincidentally in a linear fashion, right? Okay, now there's a couple reasons why I don't think that that's the case. One of the reasons is that I said that we knew how much energy was being input based on how high we raised the car, right? So we know, say at this sixth position, that this has 6 times the energy as it did in this number 1 position, right? Now, if we did have a consistent amount of friction all throughout, then we would expect to get this result, this exact result. That if the resistance is constant, then we're not going to see we're going to see the car go effectively the same amount further for each increase in the height, right? So it's like, 6 units of energy gets you this far, 5 units of energy gets you this far. So it matches up nicely. The distance that we get on the straightaway is essentially proportional to exactly the height, right? Now if that isn't because the resistance, the friction is and reduction of kinetic energy is, you know, not the same, then it would be, quite a coincidence that there's enough friction to make it mask, such a humongous difference in here. So to try and address that, I wanted to see whether I could measure the amount of rolling resistance on this toy car at different speeds and see what would happen. So I went to my local fitness gym and put this experiment on a treadmill with a scale to see what would happen. So let me see whether I can bring in that video. Okay, there's this video here. And so I've got the treadmill here. And what I have is I have my car connected to a string, and I've got it connected to a very sensitive gram scale. So when I put the car on the treadmill, I can measure what the gram force is. And for this particular experiment, it was about 5 grams. And I'll tell you that the scale bounces wildly when you're doing this experiment, so it's really hard to get a straight number. But in spite of those challenges, I tried it at 1 mile per hour. I tried it at 5 miles per hour, 3 miles an hour. And it seemed that no matter, which mile an hour it was, if anything, it seemed that when you had a higher velocity, that you got, marginally higher friction, which is kind of, I don't know, the opposite of what Gary was thinking. But generally, I observed that the amount of force that was exerted by the car at any speed was still around the 5 gram range. So, like I said, that was a really hard to judge experiment because the scale is just jumping around like crazy, and you kind of have to average it with your eyeball. But I didn't see any huge indication that the friction rolling resistance of the car varied greatly with its velocity. Now, once again, it could still be. I mean, this is what would have to happen, is that the rolling resistance of that car would have to be enough to fully compensate for it not reaching these distances. And I don't think that that's possible. So, for all these reasons, I feel that that this data is good, and that the kinetic energy of an object is proportional to its velocity, not velocity squared. Now, one interesting factor is that, say, in the ball drop experiment, so, Gary mentioned that, the velocity doubles when you increase the height by 4, because there's a standard acceleration formula. And that's what it tells you, that in order to get twice the velocity, you have to be 4 times the distance. But another curious thing I found is that the acceleration formula itself doesn't seem to work, because in my data here, I had the initial position at 5, but when it doubled to 10, I was actually only at the third. Only 3 times as high produced a doubling of the velocity. And when you got to 4 times, we're talking about 2.3 to 2.8 times faster, right? So it's going faster than twice as much, right? And so these two kind of balance each other out, because and I think when they did, like, say, the lead ball, I mean, the ball against the clay, they probably didn't have sophisticated high-speed cameras that they could, objectively measure. They assumed, just like we assumed the kinetic energy formula is correct, they assumed the acceleration and gravity formula was correct. And curiously enough, it doesn't seem to be correct. I did try to do some direct ball drop experiments, and these are even harder to do because even using a high-speed camera at 90 frames per second, the ball, when it goes to the frame, looks like this big old blur. And yeah, it makes it hard to measure, but I did get some similar results. And I got some conflicting results initially, but eventually, when I in my final setup, which I have the data over here, found that when you're at 4 times the height, you're actually going something like 2.8 times as fast. So the thing is that they thought the ball drop demonstrated 1/2 mv squared, because they thought that at 4 times the height, it generated a hole which is 4 times as big. But the thing is like, duh, because you just put in 4 times the amount of energy by lifting it up to that, so you would totally expect that it's gonna just put the dent in, it's gonna be 4 times as large, right? You don't need you don't need 1/2 mv squared to explain that. And if they had actually measured the actual velocity of the ball when it hit the clay, they would find that it would actually be going something at like 2.8 times as fast, and not 2 times as fast. So that ball drop experiment really didn't confirm the kinetic energy formula, because you have to measure the freaking velocity in order to do that, right? You have to confirm the velocity at impact time. And I'm sure that they had no way of doing that without high-speed electronic cameras, okay? But I have high-speed electronic cameras. I have access to the internet. I have things that people 100 years ago would never dream of having, just sitting in their house. But yeah, I know the results here are extremely, extremely controversial. I know that my mainstream friends are all going to say this guy is crazy. But if you think I am, then I challenge you to prove that I am wrong. And you do that by repeating this experiment and seeing whether you get the same results. That is a primary cornerstone of proper scientific procedure, is that one guy does an experiment, the next step is another guy does experiment, see whether he gets the same result. Or if you think my analysis is wrong, show that my analysis is wrong. For example, show that the frictional resistance of some object like this toy car does vary with the velocity in such a way that it completely cancels out the v squared formula and turns it into mv, right? But I'm probably more convinced that the kinetic energy formula is in fact mv, which is what is commonly known as momentum. And as Gary points out, historically, Newton, we love Newtonian mechanics. Newton apparently thought that kinetic energy was mv as well. And apparently, if what Gary says is true, that if you are doing something actually practical, like trying to put a spaceship in orbit or maneuver something, you have to use mv and not 1/2 mv squared. in order. So NASA uses MV, right? They don't use 1/2 MV squared, because if they did, they might find that there's a problem. I mean, but in most cases, I'm thinking that that the fact that this formula is not true doesn't make a heck of a lot of difference in most people's lives, right? Not unless you're trying to design some sort of machine that, for example, I don't know, maybe you're trying to punch a hole in some thickness of material, and so you have electronic punch, and then you figure, oh well, I want to go punch something that's 4 times as thick, so I'll just dial my puncher so to double the velocity, right? And then when I do that, I find out, no, that's not enough. That's not going to work. So you have to dial it up to like 2.8, and then it has enough velocity to actually punch through, because that's the speed you need that you would get if you had actually 4 times the energy, right? So you put 4 times the energy. But it is shocking that things like possibly the acceleration of gravity formula is wrong, as a corollary to why the kinetic energy formula is wrong, and how our belief in either or both of these, kind of misled us to think that. So, if you made it this far in the video, I hope I've convinced you through experiment in my MIT diploma that the most beloved formula in physics is in fact wrong. And once again, if you think I'm wrong, prove it. Do another experiment to prove it, or show me what was wrong with my experiment. Once again, this is now the only experiment on the internet, on YouTube, which attempts to directly measure this thing. You show me any other experiment which directly tries to measure the thing and comes up with some mechanism for measuring the amount of kinetic energy in a moving object. That's what you'd have to show me that I'm wrong versus the kinetic energy formula. So good luck to everyone, and this just all goes to show you that we cannot rely on using math. So for example, if you went on the internet and you Googled, how to prove the kinetic energy formula, what you end up finding is just a bunch of videos that like derive the kinetic energy formula from like the work formula. They all look like stuff like this, kinetic energy, and it's all about solving equations and stuff like that, but no actual experiments. And so that is what I am justifying by making this video, which is an actual physical experiment. All right. Now, if you're interested in any of my data, any other information, please leave it in the comments, and we'll see if we can get this all figured out. But that's all I have for you for today. I think that was quite shocking enough.